distance is, let's suppose, 3 meter. This is also 3 meter only complete. Now my question is, where should I keep a 5 kg object so that that means from this distance I'm asking, that it should remain in equilibrium. Find x so that system remains in equilibrium. Just try for 1 minute, then I'll solve. So after,
No, sir, I'm not understanding.
okay, now this question is based on principle of moments. That is the next topic that you can see here. So what is principle of moment, Neil? That for equilibrium, net torque should be zero. Net torque should be zero. Force is zero because it is fixed, no problem in that. But net torque should also be zero. Now 2 kg is applying force, that is weight of the body, that is 2g downward, and 5g is applying force here, that is 5g. Okay,
Oh,
so you see one force is try to rotate it anti-clockwise, and this force is trying to rotate the rod in clockwise. Okay,
okay,
and
okay.
axis is here only, this is the axis. So if I try to find the for equilibrium clockwise torque, clockwise torque is equal to anti-clockwise torque. Anti-clockwise torque. Then only the net torque will be zero. Now torque formula is force into distance. This distance is given as 3 meter. So force is how much? 2g. 2g means 2 into 10, 20 Newton. And this is 5 into 10, that is 50 Newton. So I can write that 20 Newton, and the distance is from the axis is 3 and the angle is 90 degree. So 20 into 3, and here it is 50 Newton. And distance, let's suppose from the axis I have taken as x, and there is also angle 90 degree. That means what we get, that x is equal to 60 divided by 50. That means x you should keep at 1.2 meter. So if you keep this 5 kg at 1.2 meter, the system will remain in equilibrium because net torque becomes 0. Understood? Okay, Neil, please tell. Neil, are you there? Neil, you are mute? No. Yeah. Now tell. Understood or not? I can't hear you. Madam, can you hear Neil? Hello, ma'am. Are you there? Hmm. Neil, you are not mute. You are unmute, but then also I cannot hear you. What's happening?
Hello, sir. Now can you hear me?
Yeah, now I can hear you. What was happening?
Sir, internet issues happening on the laptop. I don't know. So I've joined
Okay,
from the phone.
okay. Now I can hear you. So
Or
I want to, I want to go in your exercise, question number 80. You have the target book with you?
yes, sir. Could you just scroll upwards for 1 minute?
Yeah, sure, sure.
Yes, sir. Done.
Okay, go to exercise and question number 18. You see, one example is given that one rod is like this, and it is fixed at this place like this. This is the support. Now here this is 12 kg, and here is M, and here is 3 kg. This distance is given L, I think. Okay, I think no, support is not here. No, it's correct only. L. Yeah, correct. This is L only. Support is here only L. And then this is given L by 2. And from there it's given L. Can you see this question, Neil?
Yes, sir. Yes, sir. I found it. I think.
And they're asking what is the value of M in equilibrium. The system is in equilibrium.
Sir,
Yes,
example
sir.
18 in which page number?
It's not example exercise, page number 62.
Okay, okay. Oh,
Ah.
okay, sir. Found.
So here you have to find the value of M. And this is the support where we have fixed. This is the axis. What I should do, I should find the torque, right?
No, it's showing we have to find the value of mass M.
Yes, for that we have to find the net torque,
Yeah, for
and
that.
net torque will make zero because it is in equilibrium, and then we can find the value of F, right? So
Right, right.
if I take this as the axis, then 12 kg means its weight is 120 Newton. It is acting downward. So it tries to rotate the rod in anti-clockwise manner. Mg is acting downward and Mg will try to rotate in a clockwise manner. This is also acting downward, that is 30 Newton, and trying to rotate clockwise manner only. So there are two clockwise torques and there is one anti-clockwise torque. Can you see that?
Yes, sir.
And our concept is clockwise torque should be balanced by anti-clockwise torque. Clockwise torque should be balanced by anti-clockwise torque. So clockwise torque 2 I have to find. First mg as a distance, force is mg and distance is L by 2. So this is mg multiplied by L by 2. Angle is 90 only. And one more clockwise is 30 into L. This is 30 and the distance from the axis is not L. I have to take the complete distance here. So it becomes L plus L by 2. L plus L by 2. And anti-clockwise is only 120. So this is 120 and distance from 120 is L, from the axis is L only. By solving this, tell me, Neil, how much you are getting as M. Which option is correct?
Okay, sir. 1 second.
G, you can take 10 here. So this is 10 ml by 2. This will be 3L by 2. 3 into 3 I can use 90 L by 2. And this is 120 L. L I think you can cancel. So this is here 5M plus this is 45 and this is 120. So it means 5M is coming as 75. That means M equals to 15 kg. Second option should be correct.
15. Huh?
Okay.
Yes, yes, sir.
So this equilibrium concept is clear.
Yes, sir, it is clear.
Now dynamics or equation first. Let's understand. Before equation, one more thing I want to tell, that is relation between torque and moment of inertia. Moment of inertia already we have discussed. Torque we have completed. Now what is the relation between torque and moment of inertia? So if I take, let's suppose I have a particle which is moving in a circle. This is a particle of mass m here. It is moving with some velocity omega. So it has two forces acting here. One force is centripetal and other force is tangential. I know that centripetal force will not produce any kind of torque. Why? Because it is intersecting the axis. It is going along the R. If this I'll take is R, any force that is along R does not produce any kind of torque. So centripetal force does not produce any torque. Does not produce any torque. So tangential will produce the torque, and tangential torque I can write as force tangential into distance from the axis is the radius itself. Radius I can take R, angle is 90 degree. Now tangential force formula, we know that mass into acceleration. Acceleration is formula of tangential acceleration formula. If you remember, tangential acceleration formula is R alpha. R alpha. So m into R alpha into R. That means torque we are getting as this is m R square into alpha. Now m R square is moment of inertia. So I can write the formula as torque equals to I alpha. That is the equation or relation between torque and moment of inertia. If you remember in translational motion, we used to write F equals to ma, Newton's law. In rotational motion, F becomes torque, mass becomes moment of inertia, and acceleration linear becomes rotational acceleration alpha. Okay.
Okay, sir.
So any question if you want to solve on based of equation, what is the angular acceleration? You can use alpha is equals to torque divided by moment of inertia. This equation we can use. And you can also use the equations. What are the equations that we can use? Equations of uniformly accelerated rotational motion. Rotational motion. Equation of uniformly accelerated rotational motion. So for that, in linear motion, we use V equals to U plus AT. And here I can write omega is equals to omega naught plus alpha. That is, omega is final angular velocity, omega naught is initial angular velocity, alpha is the angular acceleration, that is torque divided by moment of inertia, and t is the time. Okay, understood?
Understood.
And the distance equation we write as ut plus half at square, so that we can here write as theta is equals to omega naught t plus half alpha t square. Here you can write v square equals to u square plus 2as. Here you can write omega square equals to omega naught square plus 2 into alpha into theta. You can also write the distance in a particular second, that we write as s nth second, and its formula was in linear motion u plus 2n minus 1 by 2 into a. So here also angle rotated in a particular second, if they ask, then we can use the formula omega naught plus 2n minus 1 by 2 multiplied by alpha. Is it clear?
Yes, sir. Clear. Could you just scroll up for 1 second?
Yeah, sure, sure. Yeah.
Yeah. Yes, sir. Done.
Understood?
Yes.
Okay. Now, one question I can see here. That is page number 63, Neil.
Yes, sir.
And the question number is 29. A wheel starts from rest and attains an angular velocity of 20 radian per second after being uniformly accelerated for 10 seconds. The total angle in radian through which it has turned in 10 seconds.
Yes, sir.
Okay. So what are the parameters given? Starts from rest means omega naught is 0, right?
Yes.
And angular velocity final is 20 radian per second. So omega is given as 20 radian per second. And after being uniformly accelerated for 10 seconds, time is given as 10 seconds. And I have to find the total angle in radian through which it has turned. That means theta we have to find. So first you can find alpha because theta, you can use two formula here. One formula is omega naught into t plus half alpha t square. For that you need alpha. Alpha you can find by the equation omega is equals to omega naught plus alpha t. Omega is given 20, this is given 0, alpha we don't know, and t is given 10, and that gives alpha equals to 2 radian per second square. 2 radian per second square. Okay, understood?
Yes, sir.
Now, if I put the alpha value here, omega naught was 0 only. Alpha, if I put here t, then this is 10 square. So you get the answer 10 square, that is 100 radian is the final answer. Okay.
Okay.
Another method is there to find theta. You can use initial velocity plus final velocity divided by 2. This is called average velocity. Average velocity multiplied by time. So initial is 0, final is 20 divided by 2 multiplied by 10. So this is 20 by 2 will be 10 only. 10 multiplied by 10. By this method also you get the value as 100 radian. So for any one of these two methods you can use. Okay.
Okay, sir. One second. Okay, sir. Done.
Okay. So now let's go to the next example. Now let's take a few application based question like if I take a pulley here and this pulley is fixed, and in that pulley let's suppose one rope has been wrapped like this, and that other one end is end of the rope is fixed here, other end is connected with one block of mass, and this pulley is having a radius r, and it has a moment of inertia as I. Normally pulleys are in the shape of cylinder, but it can be given wheel also. If it is wheel, then it is a ring, otherwise it is a cylinder. They can ask you acceleration of mass m, or they can ask the distance traveled by m. If you know the acceleration, anything other you can find very easily. So how to proceed with this question? I'll take one example here. First, you understand the dynamics part. Like m is going down, so why it is going down? Downward force will be mg, right, Neil? And tension will be T, and if its acceleration is A, then one equation is very much sure that mg minus T is equals to ma. Do you understand this example, Neil?
Yes, sir, I understood.
Okay. And then here also tension for the pulley also I have to write. If this is the tension, this is the radius, angle is 90 degree, then due to this tension, the wheel is rotating with some acceleration alpha, let's suppose. So here we have to write net torque, torque on pulley. This is block equation. You have to write the pulley equations also. So pulley equation is T into R, that is torque, angle is 90 degree, is equal to I alpha. This is tangential acceleration that I have taken alpha, and that that acceleration tangential always you can write as R alpha. So in place of alpha, I can use A by R, because the acceleration downward I have taken A, and this is tangential only. Tangential acceleration is A. So alpha I can write A by R. So it becomes what? T into R is equal to I into A by R. R, if I take this side, Neil, it becomes T is equals to moment of inertia into A by R square. So this I make as the second equation. T equals to I into A divided by R square. Now I have two equations. If I add these two equations, then T will get cancelled. So what I get here? I get mg is equals to small m plus capital I divided by R square into A. So acceleration of the body should be mg divided by small m plus capital I divided by R square. And if you know the acceleration distance table, you can find by very easily, because it was initially at rest only, so you can use half at square. That is the secondary thing, but the main step is to find the acceleration. Please make a note, Neil.
Yes, sir. Yes, sir. Done.
Okay. Page number 65, Neil. Question number 46. It is based on this. Page number 65. Question number 46. You see, it is given that disk. I think it is disk. It is given as a disk, and here we have a mass m. Can you see this question, Neil?
Yes, sir, I can.
Okay, so string is wrapped and mass m is there. Speed of the block as it descends through a height h. The radius is given r here. So you know that moment of inertia, disk is also having mass m, and the block is also having mass m. So disk moment of inertia about that, because it is rotating about this axis only. So if you remember, this formula is mr square by 2. Mr square by 2. This is the moment of inertia of the disk. And they're asking that when it descends through an height h, at that time, what is the speed? So anybody, if released from rest and initial velocity is already given here, initial velocity is given here 0, and distance travel is given a h. So you have to find the velocity. So better you should use the formula v square equals to u square plus 2as. U is 0, so v square will be 2a. In place of s, it is given h. So our answer should be v is equals to under root 2a h. Now what is a? For that I have just derived a formula here. If you can see this formula I have derived. A is nothing but mg divided by small m plus moment of inertia divided by radius square. Let's use that formula only here directly. So mg divided by m plus I is mr square by 2. So let's like here mr square by 2, and this is r square. R square cancel. So a we are getting here is mg. This is 2m, 3m by 2. 2 I'll take it upward. So I am getting here in place of a, I am getting 2g by 3. In place of acceleration, I am getting here 2g by 3. So if I put this value here, then velocity should I get as under root 2 into this is 2g by 3 into h. I can take 2 outside nil because it's 2 square. The rest all will remain inside only. So 2 outside under root gh by 3. That answer I am getting. And that is option number 3 here. Please check yourself and make a note.
Yes, sir. Done.
Okay. So this concept understood?
Yes, sir.
If you have, let's suppose, instead of one string, there are two blocks, one on this side. Let's suppose one block is on this side. This is M1 and other block is this side. This is M2. M2 is going down with the acceleration A. M1 is going up with the acceleration A. The radius of the pulley is R and its moment of inertia is I. So if in case of light pulley, if you remember, both string tension were same, T only. But it is not a light pulley, so tension will be different. Like here, if I write tension is T2, then here will be tension T1. So tension we have to take different because pulley is also having moment of inertia. Understood?
Yes, sir.
And here this force is M2Z. This force is here M1G. M2 is going down, so equation will be M2G minus T2 is equal to M2A. M1 is going up, so this is T1 minus M1G is equal to M1A. And pulley, there are two torques. This T1 is trying to, this is T2, sorry, this is T2. This T2 is trying to rotate it in clockwise manner. And this torque is T2 multiplied by R. But this T1 is pulling it this way. T1 is trying to rotate in clockwise manner. This torque is anti-clockwise, but this torque is clockwise. So you have to subtract both torque to find the net torque because they are in opposite direction. So this will be minus T1 into R and net torque equals to moment of inertia into alpha. As acceleration tangential here is also A. So in place of alpha, I can use A by R. So that will be here T2 minus T1 is equal to IA divided by R square. This is equation 1. This is equation 2. And this is equation 3. Now what I'll do, I'll add both three equations. All three equations I'll add 1 plus 2 and plus 3. So here T2 minus T2 plus T2 cancel, plus T1 minus T1 cancel. So I get here M2G minus M1G, M2G minus M1G is equal to right side I have M2, then I have here M1, and here I have I divided by R square, and A is common in all. It means that acceleration equation I have got here, I can take G common, M2 minus M1 multiplied by G divided by this is M2 plus M1 plus moment of inertia divided by radius square. So in case of two blocks, you have to use this concept. Don't remember this formula, just try to understand this.
Okay, sir. Yes, sir. Done.
Okay, Neil, now energy and rolling motion is left and conservation of angular momentum. Three topics are left. So
Okay.
Sunday you have exam, na? So I need
Sir.
three lectures. I need three lectures.
Yes,
So
sir.
one,
We have one tomorrow, no? Or
but
three more lectures.
at least two more. So one
Achha.
lecture you plan in either tonight or tomorrow night. You let me know, okay?
Okay, sir.
Then two lecture, this chapter will be completed.
Okay,
Okay?
sir. Sure. Sure, sir.
Oh, bye.
Bye, sir.